Welcome to our quantum deep dive.
Great to be here.
Today, we're really plunging into something pretty exciting, I think. A very precise area of quantum computing. Ion trap qubits.
Yeah, definitely a key player.
And our guide for this is an insightful essay from Jörg Schneeppert called Ionenfallen Qubits, Precise Baustein der Quantencomputer. And you know how we operate here. We love taking these complex ideas.
Yeah, the really dense stuff.
Right, and breaking them down, giving you those aha moments, sort of this shortcut to really getting it without drowning in information.
That's the plan.
So today, that means unpacking why these ion trap qubits are seen as such incredibly precise building blocks for quantum computers.
Yeah, and what's really fascinating, I think, is just how fundamentally different they are from, the computers we use every day.
Right.
And why that difference is actually so critical for solving problems that are just, impossible right now.
Okay.
So we'll look at what they are, definitely, but also how they work, the big challenges, and, the incredible potential there.
Okay, let's start right there with that fundamental shift, because this is where it all changes, right? Classical computers, we get bits, simple zeros or ones.
Yeah, on or off.
But quantum computing brings in the qubit. So, how is a qubit really different? Why does it matter so much?
Well, the absolute core idea is that a qubit isn't forced to be just a 0 or just a 1.
All right.
It can actually tap into this quantum property called superposition, which means it can effectively be both at the same time.
The spinning coin idea, where it's heads and tails until it lands.
Exactly like that. It exists as this combination of possibilities. It has a certain probability of being 0 and a certain probability of being 1 simultaneously.
Right.
And this isn't just, a neat trick. It means a single qubit can kind of explore multiple paths or solutions at once.
So that's the parallel processing power people talk about.
That's a big part of it, yeah. It gives quantum computers a fundamentally different way to process information.
That capability alone is, mind-boggling.
Yeah.
And then you add entanglement.
Yes, entanglement.
This is where it gets really wild, almost spooky. What's so special about entangled qubits? How does that boost the computation?
Okay, so entanglement. This is where things get deeply connected. If you entangle 2 or more qubits, they become linked in this intrinsic way.
No matter how far apart they are.
Doesn't matter. The state of one instantly influences the state of the other. The source mentions an example like Fios, 1 Oros plus 11ing. If you measure one qubit as 0, you instantly know the other is 0 too.
Wow.
And this deep interdependence, this connection, it allows for really powerful ways to process information together. Ways that classical computers they can't mimic it.
Okay.
It lets you leverage these linked possibilities for complex calculations. Which, naturally leads to the question, how on earth do you actually build something physical that can hold on to these weird properties?
Right, because it sounds incredibly delicate. So there's this big race, isn't there, to find the best way to actually make a qubit.
Oh, absolutely. A huge amount of research.
And Schneeppert's essay mentions a few contenders besides ion traps. Things like superconducting circuits, photons, electron spins. Can you give us the quick rundown, pros and cons?
Sure. So superconducting qubits, they're very fast, and they can leverage some existing chip-making techniques.
Okay, that sounds good.
But the big drawback is they need extreme cold. We're talking millikelvin temperatures, colder than outer space. Requires massive refrigerators, and their quantum state doesn't last very long. They decohere quickly.
Right, limited coherence times. Okay, what about photons?
Photonic qubits, so using particles of light. They're great because photons don't interact much, so they can hold their quantum state for a long time, high coherence. Excellent for communication,
Right.
But they're really hard to get to interact when you want them to for calculations, and storing them is tricky.
Okay, and the semiconductor ones, spin qubits.
Spin qubits and semiconductors, yeah. The appeal there is potential integration with current silicon technology, like maybe eventually fitting onto regular chips.
Yeah, that would be huge.
It would, but controlling individual electron spins precisely and linking them up, it's incredibly complex, still very challenging. Each approach has its own big hurdles.
Okay, but the essay, it really focuses on ion trap qubits, positions them as a leading technology. So why? What makes them stand out in this race?
This is really where ion traps have a major advantage. Their absolute killer feature is extremely long coherence times.
Longer than the others.
Much longer. We're talking minutes, sometimes even hours in research settings compared to maybe milliseconds or microseconds for others.
Wow, okay. That's a huge difference.
It's massive. It means the qubit holds its quantum information for a very long time, which drastically reduces errors during computation, gives you more time to actually do things.
Makes sense.
Plus, they offer very high precision in operations. When you manipulate them, you can do it very accurately, leading to exceptionally low error rates.
And that's crucial for error correction later on, right?
Yep, absolutely critical. You need low physical error rates to make quantum error correction practical. Now, the trade-off is that their gate operations, the actual switching, can be slower, milliseconds maybe, compared to nanoseconds for superconductors.
Okay, so slower gates, but much higher stability and accuracy.
Exactly. For precise calculations where you really need reliability, that stability is golden.
This sounds almost like science fiction holding individual atoms.
Yeah.
How do you actually do that? What is an ion trap? Physically, how does it capture these particles?
It's pretty ingenious engineering, actually. An ion trap uses electromagnetic fields to essentially create an invisible cage in a vacuum.
A cage made of fields.
Yep. It suspends a single charged atom, that's the ion, in free space, preventing it from touching anything. The source highlights two main kinds, the Paul trap and the Penning trap.
Okay.
The Paul trap uses oscillating, rapidly changing electric fields. Think of it like juggling the ion with electricity so it stays put in the middle.
Huh.
The Penning trap uses a combination of a strong static magnetic field and a static electric field to confine the ion, sort of forcing it into a tight orbit.
Right.
Both methods achieve the same goal, isolating the ion perfectly from its environment, which is crucial to protect its delicate quantum state.
Okay, so you've trapped your ion. How does that trapped particle then become a qubit? And how do you actually do the quantum operations, the calculations?
Right, so trapping is step one. Then you need to make it a qubit. What they do is choose specific types of atoms, things like ytterbium, beryllium, calcium are common. They ionize them, give them a charge. And these ions have very stable electronic energy levels. Two of these stable levels are chosen to represent the 0 and 1 hazy states of the qubit.
Okay, so the atom's own energy levels are the qubit states.
Exactly. And then manipulate them to flip between 0 and ISO or put them in superposition. That's done with ultra-precise laser pulses.
Lasers again?
Lasers are key. They're tuned very carefully to interact with the ion and induce specific energy transitions. Often these are called Raman transitions.
Okay.
This allows for single qubit operations, basically rotating the qubit state on its own. Think of it like turning the quantum dial, but crucially, it also allows for two qubit operations.
Which you need for entanglement.
Precisely. Gates like the CNOT gate, which flips one qubit based on the state of another, these are essential for creating entanglement and running complex algorithms.
And you mentioned cooling, too.
Ah, yes, laser cooling. They also use lasers, different ones, to slow the ion right down, remove its kinetic energy. Doppler cooling and sideband cooling. Basically, getting the ion as still as possible minimizes noise and makes the operations even more precise.
Okay, so incredible precision, amazing coherence. It really does sound like ion traps are leading the pack.
They have some strong advantages, definitely.
But there's always a but, right? What are the big challenges when you try to scale these up? Going from a few ions to the thousands or millions you'd need for a truly powerful, world-changing quantum computer.
Yeah, that's the core challenge, scalability. Precision with a few qubits is one thing, maintaining it with thousands is another beast entirely.
So what breaks down?
Well, even with ion traps, gate errors can start to accumulate as you add more ions into a single trap.
Why is that?
The more ions you have, the more complex their collective motion becomes. These shared vibrational modes can interfere with targeting just one specific ion with a laser pulse accurately. It gets crosstalk.
Ah, okay. Like unintended interactions.
Exactly. And while the coherence times are great, they're not infinite. They're still susceptible to environmental noise, tiny magnetic field fluctuations, or slight drifts in the laser frequency or intensity. Even temperature changes can affect the trap stability. All these things can cause decoherence.
So maintaining that perfect isolation gets harder and harder with more qubits.
Precisely.
So if putting millions of ions in one giant trap is basically impossible, how do you get to those massive qubit numbers needed for, say, breaking encryption or designing new drugs?
This is where the really clever architectural ideas come in. The leading strategy is basically quantum networking.
Networking, like linking smaller traps together.
Exactly. Since one huge trap is impractical, the idea is to build many smaller, manageable ion trap modules or processors and connect them.
How do you connect them quantumly?
Using light. Photonic interconnects. You can get an ion in one trap to emit a single photon that's entangled with the ion.
Okay.
That photon can then travel down an optical fiber to another trap module, miles away potentially, and transfer that entanglement to an ion there.
Wow. So you create entanglement between separate traps using photons.
That's the concept. It allows for distributed quantum computing. Different parts of a calculation could happen on different modules, all linked together quantum mechanically.
That's incredible. Are there other ideas too?
Yeah, people are also exploring modular architectures where maybe several ion trap chips are linked on a larger platform, and even shuttling architectures.
Shuttling, like moving the ions.
Physically moving the ions around within a complex chip structure, bringing them together to interact when needed, then moving them apart. Imagine tiny ion highways on a chip.
Okay, these are seriously futuristic designs.
They are. But they're seen as necessary paths to overcome the scaling limitations of a single trap.
This is all just amazing engineering and physics, but let's bring it back down to earth a bit. What's the actual real-world impact? If we get these large-scale ion trap quantum computers, how might that change things for, us?
Well, the potential impact is enormous across many fields. Take optimization problems, for example.
Like finding the best route for deliveries or managing investments.
Exactly. Quantum algorithms like Grover's for searching or QAOA for combinatorial problems could find optimal solutions much, much faster than any classical computer possibly could for really complex scenarios.
So logistics, finance, huge efficiency gains there.
Potentially transformative, yeah. Solving problems that currently take weeks or years, maybe in minutes or hours.
Okay, I can see the business applications. What about science and security?
Big impact there, too. In science, the dream is simulating complex molecules.
For drug discovery, material science.
Precisely. Classical computers really struggle to accurately model the quantum behavior of large molecules. Quantum computers are naturally suited for it. This could let us design new drugs with incredible precision or discover materials with amazing properties. Think room temperature superconductors, better catalysts, more efficient batteries.
That alone would be revolutionary.
Absolutely. And then there's cryptography and security. This is the double-edged sword.
Because Shor's algorithm could break current encryption.
Exactly. A large enough quantum computer running Shor's could factor the large numbers that underpin things like RSA encryption, which protects a lot of our online data today.
So a quantum threat.
A very real potential threat, which is why there's a huge push for quantum-safe cryptography, new encryption methods that even a quantum computer can't break. And interestingly, quantum systems like ion traps could also play a role in implementing new forms of quantum encryption.
So they're both the threat and potentially part of the solution.
In a way, yes. It's definitely a game changer for cybersecurity.
So looking forward then, what's the immediate focus for researchers working on ion traps? What are they trying to improve right now?
Well, the push continues for miniaturization, making the traps smaller, putting them onto microchips to help with scalability.
Right, chip-based traps.
Yep. There's constant work on refining error correction techniques. Implementing codes like the surface code efficiently is a huge area of research, making the computations robust against those inevitable small errors.
Makes sense.
And, of course, trying to improve gate speeds. While stability is great, faster operations would obviously be better. Finding ways to speed up those laser interactions without losing precision.
Any other big trends?
I think hybrid architectures are really interesting. The idea of combining ion traps with, say, superconducting qubits.
Taking the best of both worlds.
Exactly. Maybe use the ions for their long coherence, like quantum memory or for error correction, and use the faster superconducting qubits for the quick calculations.
That's clever. Sort of a specialized team.
Potentially, yeah. And building out those quantum networks we talked about, linking traps together. That's a huge ongoing effort, too.
Well, that was absolutely a deep dive into the world of ion trap qubits.
Yeah.
Amazing stuff. We've really seen how these incredibly precise systems using superposition and entanglement,
those core quantum features,
really offer a path to tackling problems that are just completely out of reach for classical computers today.
Yeah, the ability to control individual atoms with such precision using lasers, combined with those potentially very long coherence times, it really does position ion traps as a cornerstone technology for quantum's future.
Mm-hmm.
Scaling challenges are definitely real, no doubt about it, but the solutions being worked on, quantum networking, modular designs, hybrid systems, they're incredibly innovative.
And the potential payoff is huge.
Yeah.
Revolutionizing medicine, materials, cybersecurity, optimization, the list goes on. We really hope you enjoyed this exploration and got some valuable insights into this field, all sparked by Jorgo Schneppet's work. If you do want to dive even deeper, you can find more about his research over at schneppat.de.
Definitely worth a look.
Thank you so much for joining us on this deep dive. So here's something to think about. If you could point a fully realized quantum computer at any single problem today, what challenge would you want it to tackle first? Until next time, keep exploring.